Hi everyone, welcome to this webinar, which is held in the context of the Destiny European project. I am Dario Benvenuti, a PhD student of La Sapienza, University of Rome, and in this hour I will guide you through the basic concept of process mining. We will look at the tools and techniques in that context, and we will try to learn the basics. Here you can see the outline of this talk, which will be always here on top of my head, so you don't get lost during the conversation. And let's start with a bit of introduction. So first of all, process mining is in the context of data science, which of course has its roots in statistics and covers a lot of different aspects that you can see here in the picture. And it's something very similar to data mining, which of course is becoming quite hot in these days, but that doesn't cover at all processes. And that's why process mining was born, to add the process perspective to data mining, which doesn't care at all about what's behind the data. In 1998, the term process mining first appeared, but in the software engineering field, with a particular intention about discovering models of software processes from event-based data, which is something quite specific, but that covers the most important aspect of process mining. And the first survey on process mining was published in 2003 by Van der Aalst, which is the big name in this field. And after that, progresses in process mining have been great, and that's mainly because of two reasons. The first one being that the industry is changing. For example, with Industry 4.0, data is readily available and in large quantity, so there is a lot of material to analyze. And because even the industry itself is developing a great interest in process mining. And Van der Aalst successfully built a research center in data science and process mining thanks to a prize of 5 million euros that he won. And that's something that makes us understand how much process mining is becoming important. So in the context of BPM, we can insert process mining at the end of the iteration, at the end of each iteration, and that's because it's something that can be used to extract insights from logs generated by processes, and that's quite natural to perform those kind of operations at the end of each cycles of the process development. And it can give you very useful insights for the next iteration to improve and develop something even better. So now we will look at some background knowledge that is required to be able to understand process mining, and we will start by looking at event logs. It's something quite important since process mining is based on analyzing logs, and we need to use a particular kind of logs, event logs. Here in the picture you can see a quite standard example of event log, in which we have different traces, the ones numbered by case ID, and in each trace there is an entry of the log which has some particular types of parameters. So as we can see here, there is an event ID that specify what happened. There is a timestamp that allows us to order each event. And then there are a series of properties of the event, like a name for the activity, the resource that performed the activity, its cost, and so on. The important thing to remember is that there is a minimal requirement to be able to consider a log an event log, and that requirement consists of having an activity name, a case ID, and a timestamp, which are the only three parameters really required to be able to perform process mining techniques. There is a standard called XES, which is supported by all the tools available to perform process mining, and you can have a look at that by following the link here. We will look at a lot of logs during this hour, but we will always see them in this form, which is quite simple for us to have while we look at models and techniques. And in this form, we can see that it's expressed as multi-set of traces. For example, here we have three traces composed by activities A, B, C, and D, two traces composed by activities A, C, B, and D, and only one trace composed by activity A, E, and D. Another thing that's very important to understand are that processes can be modeled in a lot of different ways with different modeling notations. Examples of that are BPMN or event-driven process chains, or UML even, for example. But there is a lot of discussing about which notions could be the best to model processes. And we could say that some are imprecise, there are a lot of them that could have varying interpretations, and Van der Aalst himself proposed explicitly to use Petri nets to model business processes, and that's because he thought that transitions can represent the activities included in a business process, while places represent the conditions preceding and following those activities. Here we can see an example of a Petri net used to model a process. And as you can see, first a take order task is executed. And then there are two activities, check count and back order, which are executed in parallel. Then, when both activities have been completed, we can execute the credit check activity. And then there is a choice. If the customer has enough credit, then the order is dispatched. If the customer has not enough credit, the decline order activity will be executed, and then it will be followed by a return stock, and the process will end. So we can use models that we already have to generate event logs, and that's something very useful since process mining in the end seeks a confrontation between a process model and its event log. So any execution of a process model produces a new execution trace that is recorded in an event log, and that can be analyzed by using the techniques provided by process mining. And to do something like that, we can do a technique called playout, which is basically picking a process model and playing the activities in an order that is allowed by the model and recording the execution traces. Here, for example, we can see that there are a lot of different execution traces that can be associated to this process model in the picture, and you can see them here falling from the sky. And in particular, here we are playing out the first one, which is the one in green, A, B, C, and D, and you can see how it's executed in the picture itself. So now that we have covered this background knowledge that was needed to go deeper in process mining, we can finally face it. So we already said that process mining seeks the confrontation between event logs, or the observed behavior, and the process model, which is the expected behavior of the process. And this is done to answer a lot of different questions. And it can be something about the past, to understand if something bad happened, or to understand what is likely to happen in the future, or why, for example, people deviate from the expected behavior, the behavior expected by the company or by the developer of the system. Or we can ask ourselves, how could we control the process better, and so on. And this big field it's covered mainly by two strategies: play in and replay. And these techniques are used in different kind of operations, and they are listed here. And we have process discovery that is used to understand what has really happened. Conformance checking, which is used to understand if the log, let's say, agrees with the model of the process. And there are a lot of other techniques that range from analysis of the performance to predictions of what will happen or enhancement. And the first one that we will look at is process discovery, that is supported by the play-in operation, which is basically the opposite of what we did previously, the play-out. As you remember, in play-out we had a process model already set, and we can use it to generate event logs by playing all the activities following the rules that we have. Here in play-in we have an event log from which we need to discover the process model that generated it. So it's the opposite operation. And here we can see an example. We have collected different traces that you can see here in the upper side of the slide. And we need to generate from those traces the model that you can see here in the bottom part of the slide. It is one of the most challenging tasks, of course. And basically, here you can see the formal definition of the problem that does not specify what kind of process model should be generated. You can generate a BPMN, a Petri net, and so on. But we will always try to generate Petri nets. The main way to do so is using the alpha algorithm, which is the first process discovery algorithm that is able to deal with concurrency, which is a very important features to support while we are modeling processes. And for example, this algorithm allows to discover workflow nets. It's very simple, and we will see that because of its simplicity, it has some flaws, of course, and can be used as a baseline, for example, to develop even other techniques that can be even more robust than it. And the basic idea behind this algorithm is to scan the event log and to look for particular patterns that could be, for example, ordering relations. So we can look at some of them. We can have a direct succession if, for example, in some trace A is directly followed by B. We can have a causality relation if A is followed by B but not vice versa. So we can say that B depends completely by the execution of A. We can have the parallel, of course, if A comes before B and B comes before A at the same time in the same trace. And we can have a choice if A never directly follows B and vice versa. For sure, they need to be in the model. There should be a choice between A and B, since they are never following each other. And here, for example, we can see some of the ordering relations that we just saw in a particular log consisting of these traces. We can see that, for example, there is a direct succession between A and B, and there is a causality between A and B, there is a parallel between B and C, and there is a choice between B and E. And you can easily see all these relations in the log. So the algorithm scans for this relation and then needs to build some kind of model using them Here, for example, we can see how each ordering relations can be used to build a part of the Petri net that will be discovered. So a sequence pattern is coming from a causality relation very easily. Here we have, for example, the parallel executions or the choice execution, and so on. And here there is what the algorithm needs to do. Starting from a log, it needs to generate the ordering relations, and then those relations should be used to produce the Petri net, for example, the model of the process. And to do so, the algorithm builds what is called the footprint of the log, and which is basically a matrix in which in each cell we will have expressed the ordering relation between a particular element of the log and every other element that appears in the log. This matrix can be used in this way. So here there is the complete algorithm if you want to look at it, but we will not go too much in detail about it. What we will need to focus on are the limitations of it. And as we said earlier, it's quite simple and it has some flaws. So, for example, this algorithm can produce a model that can be described by a workflow net that cannot contain duplicate activities, so to transition with the same activity label, cannot contain invisible transitions, so activities that are not explicitly recorded in the log. They can be, for example, silent activities, so something that is always performed under some circumstances, but it's not so relevant to be logged. And cannot contain specific complex structure, some complex constructs. So it's very useful to illustrate the main ideas behind the process, being it finding ordering between activities, building a footprint, and using it to build the model. But we need in some way to cover those limitations. And that's why different extensions for it emerge, like the heuristic miner and the region-based miner. And these techniques try to overcome its weaknesses and are implemented by the main commercial software. For example, we could use Disco, which you can download and install from the link here in the slide. And maybe through your institution you could even obtain an academic license. And basically it is a process discovery tool which is based on the fuzzy miner instead of the alpha algorithm, which is very suitable to mine less structured processes that exhibit a large amount of unstructured and conflicted behavior, which is something that the alpha algorithm would struggle with. And it includes a lot of different features to perform, and we will now look at a simple demo of it. So let me just switch to Disco. So here we are with Disco, and we want to look at its functionalities to perform process discovery. In particular, here I have a dataset which can be downloaded from the Coursera Wanderers course about process mining. And as you can see here, the log is quite long and is an Excel file, which has simply a lot of entries, each one representing a particular activity. And we have something that very useful here, which is labels to understand which of the columns is the case ID, which is the activity, the timestamp, and so on, which is something very important while using Disco, and we will see in a moment why. And this is prom. Here, the first thing that we are asked to do, of course, is to load the data. As you can see here, we have the possibility to load our own data set, and we will do just like that. In particular, here I have the Excel that I showed you earlier. I can open it, and this is a very important step of discovery, in which we need to tell Disco which column is the case ID, which is the activity, and so on. Here in this case, since the Excel file was already labeled, Disco is able to do that on his own, but not always it will be the case, and so you will need to assign to each column the right property. Here you can see which column to configure, and you can see if you select one column in particular to which label is paired. So here the first column is paired to the case, the second one is the activity name, the third and fourth columns are the timestamp, and all the other ones, except for the last one, which is representing the resource that performed the activity. So these 4 columns here are just extra information that could be used but are not mandatory for the process of discovery. So once everything is done, once we have assigned the right label to each column, we can start the process discovery process by clicking on Start Import here on the bottom left. It will take a bit of time. And here you can see the process model that Disco has discovered. The first thing, the particular thing about Disco is that you can even customize the discovered model. Here on the right hand side, there is the detail pane, in which you have these 2 sliders, activities and paths, which can be moved. And basically with these 2 sliders we can adjust the simplicity and of the model, and we will look just after this demo the quality criteria that are important to consider while let's say evaluating the discovered model. But it's quite simple to understand the simplicity, even if we have not talked about it yet. For example, here, if we increase the detail of the path slider, you can see that the model becomes more complex. Of course, it's more detailed, it gives us more information, but at the same time it's becoming more complex. And if we set it to the maximum, both sliders to the maximum, we can see something very famous in this field, which is so-called spaghetti model, which is basically referring to a bowl of spaghetti in which all the paths are interconnecting, and it's becoming quite a mess to understand. So at this level of detail, even if we have a lot of insights in front of us, it's becoming quite useless to look at them, since the model is too complex to be able to be understood. So for example, if we look at what we had before, we had the details about paths at 0% and details about activities as 100%, which is the default of Disco, and which gives us this quite simple model, really easy to understand, that can nonetheless give us a lot of informations. And here in the model we can highlight both activities and transitions between them, to look at more detailed statistics, for example, about the frequencies and about performance, so the duration, the total duration, the median duration of one instance, and so on. And another really important feature of Disco is the possibility to perform an animation. Click on that button. We have the same model as before, but we can basically replay, which is another technique that we will talk about just in some moments. We can replay all the traces of the log. So basically we will visually see how activities are performed using a virtual time that is derived by the timestamps. We can adjust even the speed of this animation. And this can be very useful to understand a lot of things. For example, here we can see that there are, in particular, 4 paths which are very crowded, always very crowded. And in some processes, this could be quite a symptom of bottlenecks, or at least of particular activities that are quite complex to perform and that should be watched carefully. And we can have even a look at how activities arrive to the process. For example, here you can see that at the beginning, so in this path here before the inbound call, if we go just back to the beginning, you can see that the entries are arriving to the inbound call, which is the first task, in batches. So this is something very typical of some type of processes to elaborate activities in batches. And it is a nice insight that we can derive from this animation. And so on. So let's exit the animation. And furthermore, we can look at statistics about the model, about the performance of it, and it can be on the general level, so about the whole model, and it can be even about single activities or about resources. So it is a very powerful tool that can be used to analyze a lot of different techniques, a lot of different aspects of the business model. For example, here we can look at how much each resource is used in what is observed by the log. We can see that Samuel is the most used resources. For example, we can see the mean duration of the task performed by him, and so on. Or we can look at activities and see the frequencies with which each activity is performed, the duration, and so on. In the global overview, we can have a lot of insights. For example, we can see how, as we said before, that this kind of process presents a lot of spikes in activities, and this can be caused by the fact that they work on data in batches, and each batch corresponds to one spike here on this events histogram. And we can look even at how much activities we have over time, and here you can see that we have some spike here in the middle, and then once we have elaborated all the data, we are basically doing less work. And we can have all kind of statistics. And basically that's it. This was quite a short introduction of Disco. Of course, the tool is very, very powerful and can be used for a lot of things, and I highly invite you to download it, to load whichever kind of logs that you can find on the internet, and play with it to look at all the tools that it offers. And here we are back to the theory. We were talking about process discovery, and one important thing to know is that the main problems behind this technique are noise and incompleteness. basically this means that, of course, since we are building the process model starting from the event logs, we need to consider that, generally speaking, those logs could contain only a fraction of all the possible behavior. Or at the same times, they can have more behaviors than the one expected. So, for example, the noise is a particular kind of behavior, a very rare and exceptional, that appears in the event log, but which is not representative of the typical behavior. So it's something that we are not interested in, but instead it's present in the event log. While incompleteness is the problem of not having enough events in the log to discover all the underlying control flow structures. So here we can have a picture of this idea. We can see in the picture that the traces in the event log are in general a subset of all the behavior, which includes the noise, which is this other subset, which is between the bigger rectangles and the inner ones. So the one that we target, of course, is the, let's say, the traces that we have in the event log with some of the external activities that are not represented. So in general, there are four qualities of a result of process discovery that we need to think about. The first one being, of course, the fitness. The discovered model should allow for the behavior that is seen in the log. That's something that should always be so. And here you can see in the picture that, for example, if we found a model that can represent only a subset of the behavior that is expressed in the event log, we have in front of us a non-fitting model, since we cannot replay every trace that we already have. And we need to think even about precisions. So the discovered model should not allow for behavior completely unrelated to what was seen in the event log. So it's kind of the opposite situation. With fitness, we had a model that we was worried about having a model that could not allow for some observed behavior to be replayed, while here with precisions, we are thinking about the opposite. So to have a model that could allow for not observed behavior. And you can see in the picture here that our model is a superset of all the observed behavior. And then we have generalizations, and this is something that is mixing the first two qualities. And as you can see in the picture, for example, we should not have a model that can allow only for exactly the observed behavior, should be more general. And finally, we have the simplicity. So, of course, the discovered model should be as simple as possible, should not be more complex than needed. And now we can take a look at some of very famous models. The first one is the flower model, which is particular since it has a perfect fitness and is very simple, but at the same time it's quite useless. And it has only one place from which every activity can be performed. And of course, you can imagine that a model like that is quite useless, since from whichever state we can perform whichever activity, and even if it has perfect perfect fitness and simplicity, it gives us no insights on the process behind it. Next, we can see another famous model, which is this one, in which every place is followed by only one activity. And even if this is very, very simple, at the same time, it's not fitting, since, of course, it is representing the most frequent trace in the log, so it's very precise, but it's the only trace that can be represented by the model, so at the same time it does not generalize, so it is not fitting. This is another one in which we have that it lacks precision, since it allows for traces very different from what is seen in the log. So we have, for example, this trace A, B, 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 F, 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 G, which is possible following the model, but is not present in the event log. So we are in an underfitting situation. And another example is the opposite, so the overfitting situations, in which our model is basically enumerating all the traces in the log. So, of course, each trace can be reproduced in the model, but at the same time, we have no insight of the generalization. We can represent only the traces that we have observed, and nothing else more. And here, finally, we can see a good model that perfectly balances between precision and generalizations. So, in the end, of course, we need always to think about all this for quality and to understand if the discovered model is good enough. We need to understand if we have in it the right trade-off between all these qualities. So, going back to the process mining techniques, the next one that we're going to see is the replay, which is something very similar to play in and play out, and is used to basically reproduce a particular trace of an event log in a process model. So it is a technique that requires us to have both an event log and an already discovered or designed process model. And in this way, discrepancies between them can emerge and can be detected and quantified in a process called conformance checking. Here we can see an example of replay in which we have this trace A, B, C, D, which is basically reproduced in the model. And as you can see here, we have all the transitions from places to activities, and we can reach the end without any problem. Here instead we have an example in which the replay is not possible. So we have this trace A, C, D, and we can see that we can perform A, we can perform C, but then to perform the activity D, we should have a token here in the place P3, which we don't. And so we have a problem because we are missing a token. And furthermore, we have this token that was produced by the activity A in place P1, which is left behind and not used. So this trace had actually two problems. And using replay, those problems emerged. We detected them, and now we can perform some diagnostics using this insight. So the general idea behind conformance checking is to do so. Have a log trace, have a process traces, and check for non-conformity by analyzing them, combining them together. This can be useful to perform diagnostics, so comparing a log to a model or vice versa to get insights. So for example, we could use some global conformance measures that exist, and we can perform it to have a business alignment information, so to make sure that the systems and the real business processes are aligned, and we can use them to perform auditing, which is an activity about checking if a particular business process is executed within certain rules which are enforced by managers and governments. And we can understand, for example, if we have a wrong model or if we have a wrong logs. And the main technique used to perform conformance checking is trace alignment, which investigates the relations between moves in the log and moves in the model to understand if they align well. So here, for example, we can look at a trace. The particular trace is A, B, AD, BC. And we can have this model here, this Petri net. To perform this trace alignment, we need to see if we can perform each step of the trace in the model. So we start by A. A produces here these two tokens. In the log, then we have D and B. But unfortunately, here in the model, there is no D. So we cannot reproduce it, and hence we place here this symbol that represent a no activity move, and we go back to B, which is an activity that can be performed in the model, C, that can be performed, and in the end there is no other trace in the log, but there is indeed an activity that can be performed in the model. So we have the opposite situation. We have a move that was performed only in the model. And all these no moves operations, of course, can have a cost associated with them and can be used to detect insights. Here there is another example of an alignment in which we have, for example, this trace A, B, D, E, and G that can be perfectly reproduced in the model N1. So we have a perfect alignment. And the most important thing to understand is that for the same trace and the same model, there exist several different alignments, which can be different one from another. Here, for example, we can see the perfect one that we saw before. We can see one in which we have one move in the model only and one move in the log only. And in the end, we can see the worst case possible, which is the alignment in which first we have all the moves only in the log, and then we have all the moves only in the model. So, as we said earlier, we can assign costs to moves. In particular, we can assign a cost to a move in the log only and a move in the model only, while if the moves corresponds, are executed both in the model and in the log, we let's say we are not giving, we're assigning a cost of 0 to that situations. Of course, we can use any cost structure. And now that we have this notion of cost, we can define what an optimal alignment is. And basically it is the alignment with the minimum deviation cost. And so if we look back at the examples that we saw before, the worst case alignment at the cost of 10, since we have 5 moves in the log only and 5 moves in the model only. The middle case had, had 2 deviations, so a cost of 2, and the optimal ones, which was the perfect one in particular, had the cost of 0, since each move is both in the model and in the log. There is no deviation. So from this concept, we can derive a definition for a fitness function, which you can see here is basically the cost of the optimal alignment of the trace divided by the cost of the worst case alignment. So we have 1 minus this number. And we can see here an example of how it can be computed. So we have this model, and the trace that we have is this one, A, B, D, F, and we can see two different alignment for it. The optimal one, which has a cost of 1, since it has only one deviation, which is represented here by this move in the model only. And we have here the worst case alignment, which has always all the moves only in the log, and then all the moves only in the model. So the fitness is computed by having 1 minus the cost of the optimal alignment, which is 1, divided by the cost of the worst case alignment, which is 8 in this case. And so we end up with 0.875 for this case. So a number like that, of course, since it is very close to 1, it's a nice fitness, and we can say that this particular trace A, B, D, F fits quite perfectly in the model that we have. Of course, we can extend this concept of fitness from only a trace to the whole log by summing up all the different costs. And to perform, for example, trace alignment, and but even all the other concepts that we saw, we can use this PROM, which is a software, a tool that allows for applying all the possible techniques available in the process mining field. And now we will see its usage. So let me just switch quickly to PROM. This software is quite more complex than Disco, and but at the same time it offers a lot of functionalities, and since it's structured on tools, it can be easily extended and personalized, and as time passes it will always offer more and more functionalities, and that's why it's a bit less user-friendly. And here we will start by uploading the same dataset that we used during the Disco demo, and I have it here already uploaded. And but to do so, we could simply start by uploading here using the button on the top right corner, and we can upload it and it will be placed here. So now the file that I uploaded is a CSV, as we did in Disco, and basically everything will happen in this tab here. So if we click on the play button in the top side of the UI, we will have the main component of Disco. It's composed by an input panel, an output panel, and an action one. And here basically there is the list of every tool, every plugin offered by PROM. Consider that this is a fresh installation of PROM that I'm using, so I have not added any customized plugin. This is everything which comes when you download the software. And here on the left we can add an object, and this window will pop up, and we can select the CSV that we uploaded previously. And when the file is selected as input, the middle panel will change, displaying only the actions that can be applied to the selected input. So right now, the only action that I can take is to convert the CSV to the XES standard that we saw at the beginning of the webinar. I could try to add more input object to the input, but right now I want to do what the software is suggesting me to do. So I will convert the CSV to a XES file. And we can do so. As you can see here, sorry about that, I need to do exactly what I did in Disco. So I need to tell the software which is the case ID column, which is the activity 1, and which are start date and end date, so the timestamp. And he will produce as output the XES event log, which can be already analyzed. So we can change the visualizations. Right here we can already see some statistics, so number of cases, number of events, and so on. We can look at different kind of visualizations. This one is the for example, the explore event log, which shows traces in a bit more detail. And what is of interest is that now, using this play button here, we can use this produced resources to do new operations. So now that we clicked on that button, you can see that we came back to the window that we had before. And in the input section, now we have the XES event log that we just produced. And we can now select an action that can be performed on this kind of log. And there are a lot of them. And basically, as we saw during the webinar, what we can do with just a log is basically process discovery. So as we did with Disco, we could try to perform process discovery. And for example, we can use a miner. So we can write here miner. And for example, there are a lot of different tools that can be used, a lot of different kind of miner. And we can select, for example, this one that is a tool to obtain a Petri net using the inductive miner, which was one of the extended versions of the alpha algorithm that we saw that should try to be more precise, more useful. And here you can see on the output panel what will be produced. In this case, a Petri net with an initial marking and a final marking. We can do so. And this is the Petri net that will be produced. Consider that all these files are already produced on my PC, but when you do that for the first time, it could take a bit of time to produce these files. And here, this Petri net can be already explored. So we can, even in this case, select a different kind of visualization of the Petri net. As you can see, there are quite a few of them. And again, the nice aspect of Prom is that I can already use these fresh produced resources to do something else. For example, here now I have in input my Petri net. I can do a lot of stuff on the Petri net alone, but in this case I would like to do something else. So I would like to produce a different kind of output this time. So let me just use the Petri net and add the event log this time. So now we have two input in the input panels. With a discovered Petri net and the log that have been used to discover that net, we could perform some of course, some operations. And right now I'm interested in replay. So I would like to do something like trace alignment, as we saw. Of course, with doing trace alignment with the log that was used to discover the model is quite strange and will introduce some bias for sure. But we can use it to evaluate some particular aspect. So in particular, if I use, let's say, this tool, replay a log on PetriNet for all optimal alignments, I can try to do so. He will ask me something that, since the operations can be customized, and now we need to wait just a moment for the result. And here it is. So basically what Prom has produced are all the optimal alignments that exist between the log that we uploaded and the net that was associated. Of course, as I already said, since this log was the one used to produce the model in the first place, we should not look at performance or statistics like that, but it's interesting to look at one particular aspect. Here you can see that the traces of the log are are shown and ordered with their alignment in a particular order. As you can see, as I scroll down, the number of items here in the alignment sections increases. And what is interesting is that here on the right side we have a legend. Basically, green means that we have a synchronous move in the alignment, while yellow and red means that we have a move only in the log or only in the model. And as we go down, you see that yellow starts to increase and is increasing. And so basically what we are looking at are the traces of the log ordered on the basis of how well they fit into the model, the PetriNet that we used. And that's interesting because it's showing us which are the traces that fits the best in the discovered model, and that could give us some kind of information. So as we said previously, not every model is the same, and while we apply process discovery, we can find a lot of models for the same log, and some of them may be more fitting than others, and we have those 4 quality criteria that needs to be let's say optimized in a compromise between them. And here we can see which are the traces that fits the best in the model that we discovered. So the traces that basically was used the most to build the model, let's say like that. And if we can have a different kind of model, so for example, you could try to use the discovered PetriNet to play out some new fresh traces, and we can generate new event logs, and we can use these newly generated logs to perform a real trace alignment, to discover statistics and try to understand how well the model performs, and so on. So, as I said, the tool is full of functionalities, and I highly invite you to download it, to play with it, and to try to see what you can understand from starting from simple logs or from simple models, how you can combine logs and models and perform different kind of operations. And that's it. We will switch back to the slides. And here we are back with some quick final words. As we said at the beginning, industries and organizations starts to adapt their workflow to include process mining and to actively use it to enhance their processes. And this is basically because they are starting to care about their processes and not only about data. They want to enhance their workflows. They want to understand if what they're doing perfectly aligns with what they expect to do. And they want to perform business intelligence in the good way. And that's something that is highlighted even by these two graphs, which have data collected by HSPI. And in particular, the histograms shows us how the case distribution of organizations that are applying process mining is exponentially increasing over the years. And the first pie chart let us understand which are the fields in which this is happening the most. The first one being the financials field. And that's it. This was quite a short introduction of process mining, which is a context very, very big and that can be explored more deeply, of course. If you want to get more details about everything that we discussed, you can look at this book by Van der Aalst, or you can look at the slides that you can find at this link, or you can take, for example, an online course on Coursera performed by Van der Aalst, which is quite exhaustive and very easy to understand. Here you can see the sponsor of this project. And if you want to understand more about Destiny and what we are doing and why, you can look at the information that you can find following these links. And that's all from me. Thanks for the attention.